Hello and welcome, I'm your Code Monkey. Let's learn about 3 different methods that we can use to find targets. All methods work pretty much the same for both 2D and 3D. These are applicable to just about any scenario where you need to find targets. So you can use this, for example, in an RTS where units need to find targets, or in a tower defense game for the tower to find something, or even on the player itself to enable them to do some cool abilities with the enemies that are nearby. We're going to first explore each method individually to see how they work, and then in the end we will explore the pros and cons for each method, so make sure you stay tuned to the end of the video. All 3 methods are valid depending on the scenario, so it's up to you to choose the right one for your particular use case. Over here I have a very simple demo scene, so just a normal sort of tower defense game. This scene was initially built for my tower defense AI video. So there's this tower and I can press a button to spawn some minions. They spawn on the right and they move towards the left. Now the goal is for the tower to find the enemies as they get within range and start attacking them. Okay, so let's begin with the first simplest method, which is using a collider with a trigger. Let's make a new C# script. Name this our targeting system for the collider. And let's select the tower and attach our script, okay? Now, like I said, this first method is using a collider. So let's add a circle collider. Again, if you're working in 3D, then use a sphere collider instead. Here, make sure you set isTrigger to true, since we do not want this collider to be a solid object. And simply modify the radius to get a good attack range. So maybe something like this. So as the enemy gets within that area, the tower is going to start attacking. Okay, now let's open up this script. And here this is going to be very simple. Let's just get rid of these and instead make a private void onTriggerEnter2D. Again, if you're working in 3D, then you add the onTriggerEnter instead. Now this function is triggered when another collider enters inside the shape of this collider. So it gets triggered exactly once on the very first frame that the collision starts. So let's first do a quick test just to make sure it's working. So we debug.log, just say something. Okay, let's run this and see. Okay, so here I am, and let's spawn an enemy. Here he comes, and let's look in the console as the enemy gets within range. Yep, there you go, we have our target. Okay, so with this we are correctly identifying the collision. Now, if you have issues with the collision, check out the video link in the description where I go over the various causes for issues with collisions. Essentially, you need at least 2 colliders and 1 rigid body for the collision to actually trigger. So in this case, my actual tower has a collider, the circle collider that we just added, and on the enemy, it has a box collider and then also a rigid body. So with this, we have our collision being detected. Now, we also need to identify that this object is actually an enemy. We don't want to attack friendly units that go inside this range or really any other objects. So the simplest way to identify the object that went in is to simply ask if it has a certain component. So the enemies are being made using this prefab. And this prefab also has a very simple enemy script. So we can simply use this to identify that what entered inside of our collider was indeed an enemy. So when we have the onTriggerEnter, let's do if we go into the collision and we do try to get the component of type enemy. And if this is true, then we know that we collide with an enemy. So now here, all we have to do is just attack. And now in the demo that I have prepared, I have my tower object, which has a tower script. And over here on this very simple tower script, I've got a function to set the target. So let's just call this one. So over here on the targeting system, let's first grab the tower. So private tower for the tower and grab it on the awake. So just get component of type tower. So just grab the tower, and after we verify that it's an enemy, we call set target and pass in the enemy. All right, that's it. Let's test. So here we are, and let's spawn an enemy. And he's coming, and as soon as he gets around here, yep, there you go. Now the tower is indeed attacking the enemy. All right, awesome. So here we have the very first method for finding targets. We use a collider, which can be of any shape. Here we use a circle collider, but it works with a box collider or really any collider shape. So using this method, we have a collider set to trigger. We'll listen when other colliders enter inside the area of this collider. And if so, then we have our actual target. We set the target and we attack the object. All right, so this is the very first method. Now for the second method, this one is going to be cycling through a list and testing for the distance. So let's first make a separate script. So a new C# script, call it the targeting system for the list distance. Let's select our tower, attach our new script, And let's remove the previous one. Okay. Now for this one, it is not based on a collider, so we can also get rid of our targeting collider. Now here, the one piece of data that we're going to need is the range. So let's make a serialized field for a private float for the actual range. This is our attack range. And here in the editor, now we can set the value. So let's set it to 60, which is the same we were using. And now here, let's make a simple private void update. And on update, we want to essentially cycle through all of the enemies in our world. Now for that, I have the enemy script here. And this enemy script already has a static list of enemies. So there's this list and this function to get that list. And on this list, down here on the enemy awake, the enemy gets added onto the list. And when the enemy dies, then the enemy gets removed from the list. So this list contains all of the alive enemies in the world. So here we just cycle through the whole list. So do a for each enemy in, and go into the enemy and get the enemy list. So we cycle through the entire enemy list. Then we just do a vector3.distance, calculate the distance between this transform position and the enemy transform position. And we simply do an if, and if the distance is under the range, then we have the enemy within range. And if so, then we simply attack the enemy. So the same thing, we get a private tower to get the tower reference. So we grab the tower, and here just tower, set the target, and pass in this enemy. Now in this case, our enemy list is already pre-filtered to contain only the enemies that are alive. So here we don't need to verify that it is an enemy, and we don't need to verify that it's alive. So that's it. It's this simple. Let's test. Here we are, and if I spawn an enemy, here he comes, and as he gets around here within range, and yep, there we go, we have our target. So our targeting system is indeed working. The enemy spawns, it does a vector3.distance between this position and the enemy position. If it is within a certain radius, then we have our target. All right, awesome. So this is our second method. Now for the third method, and by the way, if you find the video helpful, consider subscribing and hitting the like button. It really helps out the channel. Now the third method is using a physics call. So let's begin like we did by making a new C# script for the targeting system. And let's name this the physics overlap. Here's the tower, and let's attach this one and remove the previous one. Okay, now here, let's make a very simple private void update. And on update, the method we're going to use is the physics2d.overlap circle. Again, when working in 3D, the logic is pretty much the same, except you use the physics class instead of the physics2d. So what this function does is it asks the physics system for all the colliders that are inside of this area. So it requires a point and a radius. For the point, we just use this transform position. And for the radius, let's do it like the other script. So let's expose a certain range, and we use the range in here. And here, let's set the range to the exact same thing, so 60, okay. Now here, this function returns a collider 2D. So for now, let's just do a debug.log to see what this outputs. So a debug.log on the result of our overlap circle, and let's test. And yep, right away we do see it working. So it's doing an overlap circle in there, and right now there's no collider in there, so it's returning null. We can verify that it is indeed working if we add a collider onto the tower. So let's add just a basic box collider 2D, and yep, there you go, it does identify that collider. However, there's one thing. So it's correctly identifying the tower collider, which is indeed within our radius. However, the function that we use here returns just a single result. So it will only return the very first collision and no more. So depending on the order in which the scripts are run, that means that the enemy might be ignored. So here comes an enemy, and either the enemy or the tower won't be ignored. So right now it's only finding the enemy and not the tower. So if it had two enemies, it will only find one of them. So instead of using overlap circle, we can use the second one, which is overlap circle all. So this does the same overlap logic, except it returns all of the colliders within this circle. So we've got an array of our colliders, and all we have to do is just cycle through it. Then in here, we just need to identify which ones are the enemies. So like we did previously, we can simply do a get component. So collider 2D, try get component of type enemy. And if it is, then we do have an enemy. This is an enemy. So once again, let's grab our tower reference. So we grab the tower, and here, tower set target, and pass in this enemy. Again, you could then do all kinds of logic with this list that you have here. For example, finding the closest within the range, or just like this, which will essentially pick the last enemy within range. So let's test this method. Here we are, and let's spawn an enemy. Here it comes, and as soon as it gets about here, and yep, there you go, it does target the enemy, and the enemy does get damaged and gets destroyed. So here we have the third method fully working. This one is doing an overlap circle around this area, and as soon as the enemy collider goes inside it, then we have our collision and we have our enemy. All right, awesome. So here we saw 3 separate methods for finding targets. Now let's think about their pros and cons. Now the first method, on using a trigger collider, the main pro is its simplicity. So it's very easy, just add a collider and a single function and it all works. Very easy to implement. Another pro is how it's very visual and designer friendly. So you don't need to make any extra editor scripts. You can see the range by default. Whereas for the other methods that use a float for the range, it doesn't automatically have any visual. Yet another pro is how it's event-based, so rather than querying the physics system on every update, it simply runs the code when a collision happens, so that's much more efficient. The main con is how it requires you to add a collider onto your object. So if you use this method a lot, you end up with tons of colliders which may cause a performance impact. Also, if you already have a trigger collider, then you can't use it just like this, since you can't have multiple trigger colliders in the same object and listen to events on a specific one. So you would need to make a separate child game object with a detection collider and handle the logic there. Another potential con is how it requires working with the physics system. So if your target objects do not have colliders, then the collision event will not trigger. Those are the pros and cons for the trigger collider method. Now on the second method, the enlist distance, the main pro is that it's very easy to implement. You don't need to touch the editor at all. Everything works inside of your codebase. So for me as a programmer, this is the reason why I use this one a lot. Another pro is that it's very versatile. You're doing a cycle going through every single enemy, so that means you can easily validate more than just a position. For example, you can easily make it so one type of enemy has an attack range of 10, but another enemy of a different type has an attack range of 20. Another pro is that it's not dependent on the physics system, so you can use this method to identify objects that do not have any colliders at all. Then the main con is potential performance issues. As you can see, this method cycles through all of the objects, so if you have a handful of them, then it's unlikely to cause any issues, but as the enlist grows bigger, this starts to take more and more time to complete. So if you have 100 enemies, then this method is definitely not good. Another con is, like I said, the visualization isn't automatic. So this exposes a float for the range, and by default you don't see that in the editor. You need to guess how far it goes or make a custom editor to showcase that. And another con is also related to performance, which is that you need to run the code constantly. Now this con has a simple fix, which is to just test less often than on every frame. So if you combine it with a simple timer and search through the list at most something like 10 times per second, that helps a lot, but again, it's still more complex than the previous method, which is event-based. And the last method, which is the physics overlap, the pros and cons are similar to the enlist distance method. The main pro is that it's easy to implement, just like the enlist method. It all works through code, so there's no need to touch the editor. Another pro is that it supports massive amounts of enemies, whereas in the enlist method, it becomes worse and worse the bigger the list is. Here, it asks the physics system for the colliders within an area, so it doesn't need to query every single object that exists. And the main con is just like the enlist method, which is potential performance issues. Since this is not event-based, you need to call the function on update. If you do a physics query on every single update, then it can cause some slowdowns. But just like the enlist method, you can minimize this con by adding a simple timer and searching much less often than on every frame. Another con is, again, the visualization is not automatic, so if you want to see it, you need to make a custom editor. And another potential con is how it is dependent on the physics system. So the objects that you're trying to find need to have a collider in order for the physics query to work. If they do not have colliders, then they are not detected. Okay, so those are the 3 methods. As you can see, they all have their pros and cons. Now for me, I usually go with the second or third method. The first method requires working in the editor and modifying the game object by adding an extra collider. So after some time, you might forget which script that collider is related to, so it can become quite messy. Whereas the other 2 methods are done entirely with code, so all of the logic is in the same place. For me, as mainly a programmer, I like to keep my games through code as much as possible, so that is why I prefer those 2. Usually my approach is to use the list distance method since it's so easy to add, and then if I come across any performance issues, then I might change it to the third method. So there you have it, 3 nice methods for finding targets, each with their pros and cons. If you have other methods you'd like to use, go ahead and post them in the comments. I'm interested to see how other people handle targeting. As always, you can download the project files and utilities from unitycodemonkey.com. This video is made possible thanks to these awesome supporters. Go to patreon.com/unitycodemonkey to get some perks and help keep the videos free for everyone. If you found this video helpful, consider liking and subscribing, post any questions you have in the comments, and I'll see you next time.